Hey everyone, it's your boy Mahin. So in this video, we'll talk about binomial theorem. Now some of you probably know what binomial theorem is all about and some of you probably don't. In either cases, I hope after watching this video, you will have a better understanding of binomial theorem than what you started with. Now for those of you who don't know what binomial theorem is all about, I'll talk about it within a few minutes. But for those of you who do know about it, maybe you learned it in middle school or high school, and maybe you saw a proof of it using mathematical induction. But the problem with that proof is that even though it proves the theorem, you will not really know why it's true. You will not really know why the theorem works the way it does, right? So in this video, I will show you a beautiful combinatorial proof of binomial theorem, which in my opinion explains the theorem better than the proof by mathematical induction. Alright, so without further ado, let's get into it. Let's start with the formula we all learned in middle school or high school. A plus b whole square equal a square plus 2ab plus b square. It's probably the most widely known algebra identity ever. Then when we study a bit more, we get to know that there is also a formula for a plus b whole cube. A plus b whole cube is equal to a cube plus 3a square b plus 3ab square plus b cube. So a very natural question will be, what about a plus b whole power 4 or a plus b whole power 5 and so on? Is there any formula for this? Well, binomial theorem answers this question. Binomial theorem is basically the generalized version of these algebraic identities where n is any natural number. Now maybe some of you are wondering about this term in the expansion. What does it signify? Well, this is called a combination number. This idea comes from permutation and combination. For those of you who don't know anything about permutation or combination, don't worry, I'll discuss about this briefly before explaining the binomial theorem. So this video is not only about binomial theorem, but you can also consider it as a brief introduction to counting techniques. Now, let's notice some properties of this theorem. Firstly, there are n plus 1 terms in the expansion, because as you can see, the power of b starts from 0 and ends in n. So overall, there are n plus 1 terms starting from the 0th term to the nth term. Now what about the kth term, which represent any arbitrary term? To figure it out, first let's see what is the 0th term. Well, the 0th term is a power n minus 0 times b power 0 times n choose 0. Similarly, the first term is a power n minus 1 times b power 1 times n choose 1. So in general, the kth term is a power n minus k times b power k times n choose k. In general, we can write the binomial theorem using the summation notation like this. Here this term represents the kth term, which is any arbitrary term, and this part represents the summation of all such terms starting from k equal to 0 to k equal to n. So this is our theorem that we want to understand. Now some of you are probably wondering, is this theorem only true for natural numbers? What about when n is equal to, let's say, 1 over 2 or minus 5 or root over 2? Well, this theorem is actually true for any real number. But in this video, I will only focus on the case when n is natural number. Maybe in some future video, we will discuss the version when n can be any real number. Now, before trying to explain the binomial theorem, I will discuss a little bit about permutation and combination. For those of you who already know about these ideas, you can skip ahead. You can see the timestamp at the bottom of the video. Before talking about permutation and combination, I'll talk a little bit about the multiplication principle, which is a very fundamental idea in all of combinatorics. The idea itself is very simple. Let's say we have 3 points, A, B, and C. We have 3 different paths to go from A to B and 4 different paths to go from B to C. The question is, how many different ways we can go from A to C? Let's call these 3 paths path 1, 2, and 3. Now if we choose path 1 to go from A to B, we have 4 different paths to go from B to C. Similarly, if we choose path 2 to go from A to B, we also have 4 different paths to go from B to C. Similarly, for the third path, we also have 4 different paths to go from B to C. So overall, we have 4 plus 4 plus 4, or 12 different ways to go from A to C. We can write it differently as 3 multiplied by 4, where 3 is the number of ways we can go from A to B and 4 is the number of ways we can go from B to C. In general, if we have an event E that we can divide into several order sub-events E1, E2 up to ER, where E1 can happen in N1 different ways, E2 can happen in N2 different ways, up to ER can happen in N different ways, then the total number of ways the original event E can happen is N1 times N2 times N3 times up to N different ways. This principle is known as the multiplication principle. I want you to take some time to make sure that you understand this principle properly, as it is a very fundamental idea in combinatorics, and I will be using it in explaining the idea of permutation. Let's say we have these 3 letters A, B, C. The question is how many different ways we can rearrange them between each other. Well, ABC itself is an arrangement. Then we have ACB, BAC, BCA, CAB, and finally CBA. These are the all 6 ways to organize them. Well, what about only AB? We can rearrange it in only 2 different ways, AB and BA. Now, if you are to rearrange large number of objects between each other, it will be extremely difficult to count them like this. So the question is there a more convenient way to count this? The answer is yes. For that, we are going to use multiplication principle. Let's have a look at this box with 3 slots. How many different ways can we fill the first slot? We can do it in 3 different ways, by either A or B or C. What about the second slot? Well, for each of those 3 options, for the first slot, we can fill the second slot in 2 different ways, as we already have used 1 alphabet in the first slot. Similarly, for each of those 2 options for the second slot, we can fill the third slot in only 1 way. So using multiplication principle, we see that we can fill all these 3 slots with 3 different alphabets in 3 times 2 times 1 or 6 different ways. By similar reasoning, we can fill a box with 2 slots with 2 alphabets in 2 times 1 or 2 different ways. As you can see, the results we got here is consistent with the result that we got before by counting each arrangement manually. Let us now generalize this idea for n objects. Let's say we have n objects A1, A2, A3, A4 up to n. We have to fill these n slots using these n objects. Well, we can fill the first slot using any of these n objects. So we can do it in n different ways. Similarly, we can fill the second slot in n-1 different ways, third slot in n-2 different ways, and so on. Finally, we can fill the second last slot in 2 different ways and the last slot in only 1 possible way. So using the multiplication principle, we can fill all the n slots in n times n-1 times n-2 up to multiplied by 2 times 1 different ways, which implies we can rearrange this n objects in n times n-1 times n-2 up to times 2 times 1 different ways. Using a special notation, we can write it as n factorial. This basically signifies the number of ways we can permute n objects between them. Using this factorial notation, we can write 3 factorial equals 6 and 2 factorial equal 2, as we have seen earlier. Now, let's have a look at a slightly trickier case. Let's say we have 10 different objects. Instead of rearranging all those 10 objects between each other, we are going to randomly choose 3 objects and rearrange them between each other. According to multiplication principle, we can do it in 10 times 9 times 8 different ways, where we can fill the first slot in 10 different ways, second slot in 9 different ways, and third slot in 8 different ways. what about the generalized idea where we have n objects and we want to permute r objects out of those n objects? Well, to understand this, we are going to write this in a bit different way. We will write 10 as 10 minus 1 plus 1, 9 as 10 minus 2 plus 1, and 8 as 10 minus 3 plus 1, where these three represent the number of objects we are permuting. Using this pattern, we can write the number of ways to permute r objects out of n objects as n times n minus 1 times n minus 2 up to multiplied by n minus r plus 1 different ways. Now we can write this product as a nice formula in terms of factorial. To do that, we are going to multiply this product by n minus r times n minus r minus 1 times up to 3 times 2 times 1 and then divide by the same expression. Then by the definition of factorial, on the numerator we have n factorial and on the denominator we have n minus r factorial. The notation for permuting r objects out of n objects is npr or n permutes r. That means we have npr equal to n factorial over n minus r factorial. As we've seen earlier, when we are arranging all n objects among each other, we have npn equal n factorial. So far we have only discussed the scenarios where all the n objects are distinct. But what about the situation where some of the objects we want to permute are identical to each other and some others are identical to each other and so on? The word Mississippi is a good example for this kind of scenario. We want to rearrange all the alphabets of Mississippi between each other. But as you can see, there are 4 S's, 4 I's, 4 P's and 1 M in Mississippi. The standard rule of permutation will not work here, as in that case we have to consider the 4 S's or 4 I's or 2 P's to be distinct, which they are not. So how should we approach this? Well, the trick is to assume all the same alphabets to be distinct and use the standard formula for permutation and then divide by the same amount that we overcounted. So in case of Mississippi, we will assume that there are 4 distinct S's, S1, S2, S3 and S4. Similarly, we will assume that there are 4 distinct I's and 2 distinct P's. So as there are 11 distinct alphabets in Mississippi, we can rearrange them between each other in 11 factorial different ways. Now the 4 S's permutes between them in 4 factorial different ways. 4 I's also 4 factorial different ways and 2 P's in 2 factorial different ways. So by assuming these identical letters to be distinct, we overcounted the total permutation by the factor of 4 factorial times 4 factorial times 2 factorial. So to get rid of this overcounting, we have to divide the initial number by 4 factorial times 4 factorial times 2 factorial. So the number of ways we can permute the alphabets in Mississippi is 11 factorial over 4 factorial times 4 factorial times 2 factorial. In general, if we want to permute n objects and out of those n objects there are r1 number of one type of identical objects, r2 number of another second type of identical objects and so on up to rk type of another identical objects, then the number of ways we can permute those n objects is n factorial over r1 factorial times r2 factorials times up to rk factorials. Since the word Mississippi is such a nice example here, this formula is sometimes called Mississippi formula. Lastly, we will discuss a little bit about combination. Let's say we have 3 alphabets A, B and C. Out of these 3 alphabets, we want to find out different ways we can permute 2 alphabets between each other. We can break down this process in 2 steps. First step is choosing 2 alphabets out of 3. Second step is rearranging those 2 alphabets between each other. The first step, that is the number of ways we can choose 2 out of 3 alphabets, is called the combination number. We can write it like this and read as 3 choose 2. You can consider it as finding the number of 2 element subsets out of a 3 element set. In this example, we can choose 2 alphabets out of those 3 alphabets in the following way. As you can see, I didn't consider AB and BA to be separate, as the set A, B and B, A are identical. On the other hand, we can permute 2 alphabets out of those 3 alphabets in the following ways. In this case, we are counting AB and BA separately, as they are 2 different arrangements. So the difference between permutation and combination is that in permutation, the order of the object matters, but in combination it does not matter. That is why npn equal n factorial and n choose n equal 1. So if we want to permute r objects out of n objects, first we have to choose r objects out of n objects and then rearrange those r objects between each other. So we can write the permutation n pair as the product of these 2 steps. N pair equal n choose r times r factorial, which implies that n choose r equal n pair over r factorial, which gives us n choose r equal n factorial over r factorial times n minus r factorial. Now that we have some basic knowledge on counting in our arsenal, we are finally ready to understand the binomial theorem. To really understand what's going on, let's see what a plus b whole square really means. Well, a plus b whole square is basically a plus b multiplied by a plus b itself. If we multiply them, we get a times a plus a times b plus b times a plus b times b. I'm intentionally writing this like this instead of writing this as a square or b square to show you a specific pattern. Notice carefully the coefficient of ab in the expansion of a plus b whole square, which is 2, comes from the addition of ab and ba, which are basically the 2 permutations of ab. Similarly, the coefficient of a square and b square also come from the permutations of a times a and b times b respectively. Now let's try to do similar kinds of expansion of a plus b whole cube. If we multiply a plus b 3 times with itself, we get this expansion. Each of these terms in the expansion is basically the product of 3 factors, all possible different arrangement of a and b. Each of these a or b's are coming from different a plus b's. Now if we look at the expansion algebraically, the coefficient of a square times b, which is 3, is actually coming from the addition of aab, aba and baa, which are basically all the 3 permutations of 2 a's and 1 b. Same is true for the coefficient of a b square or a cube or b cube. Do you see the general idea now? The general idea here, which is the core idea in understanding binomial theorem, is that the coefficient of each of the terms in the binomial expansion is equal to all the possible permutations of a and b in each of the terms. I want you to take some time and make sure that you understand this idea properly. Let's try to see this idea now for a plus b whole power n. Each of the terms in the expansion of a plus b whole power n is basically the product of, let's say, few number of b's and a's. Let's say it is the product of r number of b and n minus r number of a, as the total number of a and b as factors in each of the term is equal to n. Now the coefficient of a power n minus r times b power r is the sum of all the possible permutations of n minus r number of a's and r number of b's, as all the possible permutations of a and b are present in the expansion. Using the Mississippi formula, the number of possible permutations of n minus r number of a's and r number of b's is n factorial over r factorial times n minus r factorial, which is equal to n choose r. So any arbitrary term in the expansion of a plus b whole power n is n choose r times a power n minus r times b power r, which is what we wanted to prove. Is it a coincidence that the number of possible permutations of A and B is exactly same as the formula for the combination? Well, not really. In this case, the combination formula is a special case of the Mississippi formula. We can get the same coefficient using the idea of combination. Let's say we want to find the coefficient of a power n minus r times b power r. We can choose r number of b's out of any of the n number of factors a plus b. We can do it in n choose r ways. Then we can choose n minus r number of a's from the remaining n minus r number of a plus b in n minus r choose n minus r or only one way. So the total number of ways we can choose a power n minus r times b power r is n choose r times 1 or n choose r, which gives us the same result as before. With this combinatorial explanation, you can actually see why binomial theorem is true and what it actually means. In the book named Combinatorics, a problem-oriented approach, Daniel Marcus said it succinctly. The combination number n choose k also counts the rearrangement of k's and n minus k b's, and consequently it is the coefficient of a power k times b power n minus k in the expansion of a plus b whole power n. How beautiful is that? Thank you so much for watching. If you found this video useful, consider subscribing, and I'll see you in the next video.